Welcome to tutorial number 1, Tools and Techniques Useful for Creating an Excavation Plan. If you're considering competing in NASA's Break the Ice Lunar Challenge, then this tutorial is especially for you. And if you're on the fence about whether to compete in this challenge or not, I think watching this tutorial will help ease some of your anxieties and apprehensions about creating an excavation plan. My name is Kurt Loit, and I'm a small part of the NASA Centennial Challenge's team of experts who have created NASA's Break the Ice Lunar Challenge. I'm a NASA software engineer focusing on robotic systems and other technologies that we might use in the future to support long-term human exploration of the moon.
Hi, I'm Tracy Prater, and I'm part of the team who created NASA's Break the Ice Challenge. I work in the Materials and Processes Laboratory at NASA Marshall Space Flight Center, where I support projects related to 3D printing, in-space manufacturing, and planetary surface habitats.
In this video tutorial, Tracy and I will demonstrate a chain of utilities and tools that you and your team can use to create important elements of your excavation plan.
We want to be clear that this is only one example of many tools that teams can use. Any tool or tool chains that you're comfortable using are perfectly fine and allowed by the rules.
That's right. We don't want to give the impression that we endorse certain tools and not others. That's simply not the case.
This simple flow diagram illustrates the chain of utilities and tools that we're going to demonstrate for you today. We'll start with a NASA website called Moontrack, and we'll find and save a high-resolution digital elevation model. It's an actual 3D scan of the lunar South Pole that was taken from an orbiting NASA spacecraft.
Then we'll open that digital elevation model in a Geographic Information System, or GIS, specifically an application called QGIS, or QGIS. We'll demonstrate how to perform three-dimensional measurements on our digital elevation model. We'll also zoom and crop the digital elevation model and create detailed elevation contour lines. Then we'll export just the areas we're interested in as both 2D images and as a 3D shape file.
Then we'll open the shapefile in a 3D modeling tool called Blender. We'll scan the 3D shapefile and then save it as a full-blown 3D model. If you have problems with or questions about any of the tools or utilities demonstrated here, please don't contact the Break the Ice Challenge team. Instead, reach out to the appropriate vendor using their website.
So, if you're ready, let's get started.
Moontrack is one of many online browser-based portals created by NASA that allow the general public to visualize, explore, and analyze the surfaces of other worlds using real data returned from actual NASA spacecraft.
Yeah, Tracy, these spacecraft data portals are really amazing. We get to Moontrack by searching for Moontrek, T-R-E-K. And you'll notice it's trek.nasa.gov/moon. All websites used in this video are included as links below the video for your convenience. Since we're interested in the South Pole of the moon, we can switch to the South Pole view by clicking on the little globe in the corner and selecting South Pole Map. Now we can pan and zoom to find an area of interest. Let's zoom right into Shackleton Crater, which is basically there at the very south pole of the moon. In the lower right corner of the screen, Moontrack shows the current map scale bar along with your current cursor position in latitude and longitude coordinates. You can slide your cursor around near the 10 o'clock position of Shackleton Crater's rim and see that the latitude goes to -90 degrees, which is the exact spot of the South Pole on the lunar surface. You can use this Fly To button to type in any lat-long coordinates you wish, and the map will recenter on that exact spot and highlight it with a blinking dot. Let's fly to the exact South Pole by entering -90 and 0. And there's the exact spot of the South Pole of the moon. Now, let's pretend that our mission instructions were to land at these coordinates. negative 89.5 degrees latitude, and positive 76.5 degrees longitude. And let's pretend that our mission instructions were to excavate at these coordinates, negative 89.65 degrees latitude and positive 130 degrees longitude. We can plan that mission by first typing in the landing spot into the Fly To box. And there is our landing spot. That looks relatively flat and smooth to me. Now we can type our excavation spot into the Fly To box. Oh, it looks like we'll be excavating in the center of Shackleton Crater, given those particular coordinates.
These aren't the coordinates used by NASA's Break the Ice Lunar Challenge, by the way. It wouldn't be much of a challenge if we performed the actual mission for you in this tutorial, now would it?
Good call, Tracy. I just made these coordinates up for this tutorial. In addition to map coordinates and mission planning, Moontrek allows us to look at actual spacecraft data. We can turn on and off different data layers that we're interested in studying. For example, the data being displayed right now on the map is from the Narrow Angle Camera, or NAC, on the Lunar Reconnaissance Orbiter, or LRO. We're looking at a simple monochrome photograph right now, which explains why the center of Shackleton Crater is completely black. That's because it was in total darkness when this photo was taken.
Actually, Shackleton Crater is always in total darkness, and that's due to its location at the South Pole, where the sun never rises very high above the horizon. And the fact that Shackleton Crater is quite deep with a tall rim all around makes it even harder for sunlight to find its way into the crater.
That's right, Tracy. Thanks for pointing that out. We may not be able to see the bottom of Shackleton Crater using reflected sunlight, but NASA has other ways to peer down there. Let's add a new data layer to our map. We'll click Data and we'll search for the 10-meter resolution color hillshade dataset. It's a two-dimensional visualization of the 3D laser altimeter data. This active laser sensor actually bounces laser pulses down to the surface of the moon, so this particular instrument doesn't depend on visible light in order to see. We can simply add this layer to our map and wow! Now we can see right down into the bottom of Shackleton Crater. Hey, Tracy, there are some really interesting features down here.
Yeah, we should definitely send a rover down there really soon.
Now let's go ahead and download the actual digital elevation model, or DEM, that we need for our toolchain. We'll search for LRO LOLA DEM. LOLA is the Lunar Orbiter Laser Altimeter instrument that scans and maps the surface elevation in high resolution. This result, LRO LOLA DEM S-pole 87.5 degrees, with the document icon, is the one we're actually looking for. The 87.5 degree DEM is the narrowest region of the South Pole that was scanned by LOLA, and it has a resolution of 5 meters per pixel, which is pretty amazing resolution on another planetary body. The elevation data values are referenced to an average moon radius of 1,737,400 meters, or 1,737.4 kilometers. Just click Download to start the download of this DEM file. These DEM files can be quite large because they contain a lot of data. This particular DEM file is 1.6 gigabytes. Once this DEM file is downloaded, we can open it up in a Geographic Information System, or GIS, application called QGIS.
QGIS, also known as Quantum GIS, is a popular open source desktop app that lets us view, edit, and analyze geospatial data, like DEM data, for example. This tool and others like it allow us to view the terrain details and to measure distances and slopes in 3 dimensions. It also allows us to crop out small portions of the entire high-resolution digital elevation model for use in our challenge deliverables.
Yes, cropping is critical here because the DEM file contains tens of thousands of square kilometers worth of high-resolution data, and we really only need a few square kilometers of that data to create our challenge deliverables. QGIS can be downloaded freely from QGIS.org. All websites used in this video are included as links below the video for your convenience. All we need to do in order to open our giant DEM dataset in QGIS is just drag in the file. These import errors aren't critical. QGIS was just expecting a map from somewhere here on the Earth. And there it is, our high-resolution digital elevation model of the south pole of the Moon, between -87.5 degrees and -90 degrees. It's centered on the South Pole itself.
This map looks different from the monochrome photograph that we were looking at earlier because it is different. Rather than showing reflected sunlight, this map is showing elevation or surface height.
Yes, and in this view, white areas are higher altitudes and black areas are lower altitudes. So knowing this, we can easily recognize Shackleton Crater in roughly the middle of the map, actually touching the South Pole. The rim of the crater is white because it's a higher elevation, and the middle of the crater is dark because it's a lower elevation. Now let's verify that the scale and the units are all correct here in QGIS before we try to perform any actual measurements. By looking at the description and the metadata for this digital elevation model over on the Moontrek website, we know that this dataset is 30,336 pixels by 30,336 pixels. And we also know that each pixel represents a 5 meter by 5 meter area on the surface of the Moon. Simple math tells us that if we multiply 30,336 pixels by 5 meters per pixel, we get 151,680 meters. That's the total physical lunar surface width and height of this dataset. This digital elevation model, this dataset, covers more than 150 kilometers by 150 kilometers of lunar South Pole surface area. Let's see if QGIS agrees with that number. If we double-click on the layer name, we get this very detailed Layer Properties window. We'll examine the Information tab. The extent or area of the map is showing as -75,840 to +75,840, with 0 in the middle of the map. 75,840 plus 75,840 equals 151,680 meters. That matches. So QGIS is in fact scaling the map area appropriately. That scaling information must have been stored inside the DEM file, which is pretty cool.
But what about the actual elevation data that QGIS is showing us just using these grayscale colors? Is that data actually scaled correctly and in the proper units of meters?
Good question. By looking at the Layer Properties window, the elevation data appears to be stored using a 16-bit integer rather than a floating point number. So that makes me suspect that the elevation data is in counts from the scientific instrument rather than being actually in units of meters. That's not actually an issue. It actually makes a lot of sense to store scientific data in its original raw form rather than to perform calculations on board that can be done here on the ground. To be sure though, we can perform a quick sanity check on the elevation data. We can ask our favorite search engine the depth of Shackleton Crater. It looks like Shackleton Crater is about 4.2 kilometers deep. Now let's zoom in to Shackleton Crater in QGIS and check the elevation difference between the rim and the bottom. If we click on Identify Features and then click on the center of the crater, QGIS tells us the exact coordinate that we selected, and it tells us the elevation value at that point, which is labeled Band 1. So the elevation in the middle of the crater is around negative 5,500 units. We're not sure yet if it's actually meters though. Now let's click over here on the rim, the white area. The rim is right around positive 3,000 units. Since the center of the crater is negative elevation and the rim is positive elevation, the zero elevation level is in between those 2 points. If we add these two values together, 5,500 plus 3,000, we get 8,500 units of total elevation change. I suspect that each unit is actually a half meter, which was mentioned in the Moontrek metadata. So if we divide by 2, we get 4,250 meters, or 4.25 kilometers. Well, that's pretty close to what our favorite search engine said. So right now, the elevation data that QGIS is showing us is in sensor counts or unitless, but we can easily convert that to meters. Make sure the DEM layer is selected. Then choose Raster Calculator. This will perform a calculation on a layer and save the result as a new layer. So if we double click on the source raster band name here, and then click divide by, then 2, now we have to give it a file location and a file name to save this new layer data into. I'm going to call it dem_scaled. Click OK and it creates the new layer. We don't actually need the original DEM layer anymore, because this new DEM scaled layer contains the same data only in floating point format, and the elevation data is scaled properly in this new layer. So we can safely remove the original DEM layer just to make sure we don't accidentally try to use it for any elevation calculations. We just right click on the old layer name, remove layer, OK. We can double check the scale by comparing the middle of the crater to the rim once again. The center is around negative 2,700 meters, and the rim is around positive 1,500 meters. 2,700 plus 1,500 is 4,200 meters, or 4.2 kilometers. Well, that's pretty close to perfect.
Can we perform some simple horizontal map measurements now? Measurements in X and Y across the surface? As the crow flies, so to speak. If crows could fly on the moon, that is. Gotta watch out for those moon crows.
That's super easy in QGIS. Just click View, Measure, Measure Line. A dialog pops up. Make sure you're in Cartesian coordinates and pick 2 points with your mouse. I know Shackleton Crater is about 21 kilometers across, so I'm going to start there. Click on the white on one side, which is the rim, and click on the white on the other side, which is the rim on the other side, and then right click when you're done. If we switch these units to kilometers, we can see that it's very close to 21 kilometers. It's that easy to perform horizontal or XY map measurements. You can choose a line at any angle, and QGIS will calculate the straight line length for you. You can even select a multi-segment polyline, and it'll calculate the length of each segment. You can measure areas and angles just as easily.
That's great and so easy. Can we do some simple vertical measurements now, meaning elevation or Z measurements? For example, I wonder what the slope is driving down into Shackleton Crater. Can we actually drive a rover down that crater slope?
That's pretty simple too. Make sure your DEM scaled layer is selected. Click Raster, Analysis, Slope, Run. Now we have a new layer called Slope. When we zoom in to Shackleton Crater, we can see there are some whitish stripes running up and down and diagonally across the slope map. These are sensor noise artifacts and data stitching artifacts. The DEM file we downloaded from Moontrek is essentially raw spacecraft sensor data for use by scientists, which means that it is not cleaned up nor smoothed out.
I'm definitely not an expert on the Lunar Reconnaissance Orbiter, but I suspect that the sensor noise is amplified in this 10 o'clock region of Shackleton Crater's rim, because this is the exact spot of the proper South Pole on the Moon. So the spacecraft possibly took a lot more readings in this particular spot.
I like that theory. If you look on the internet, you can find other DEM sources on other sites that contain the same Lunar Reconnaissance Orbiter sensor data after post-processing and cleaning up. Teams can use that data if they prefer a processed version. Let's focus on the slope here at 12 o'clock, which has less of those crisscrossing data artifacts. When we zoom in, we can see the crisscrossing artifacts here too, but they're less disruptive. Ignoring these crisscrossing artifacts, let's use the Identify Features tool to see what value these smooth gray spots have. Remember, the data found in band 1 in this slope layer is not elevation. This is now slope data in units of degrees. It looks like it's right around 30 degrees, give or take. We can perform a quick sanity check on that slope calculation by going back to the scaled DEM map. Just unclick the slope layer to see the scaled DEM layer beneath it. Zoom to where you can see both the light-colored rim and the dark crater floor. Make sure the DEM layer is selected and select the Identify Features tool. Let's pick two different points in this 12 o'clock area of the crater wall. One point a bit down from the crater rim. That's an X of 7908 meters and a Y of 1970 meters and an elevation of 370.5 meters. Remember, the DEM layer is showing us elevation. And now we will pick a second point a bit up from the crater floor. That gives us an X of 8141 meters, a Y of negative 1271 meters, and an elevation of negative 1659.5 meters. Now, we just do the math to calculate the slope between these two three-dimensional points. In elevation change or vertical distance, we went from positive 370.5 meters to negative 1659.5 meters. So that's 2,030 meters of vertical drop. That's called the rise. I tried to stay roughly in the same x-coordinate when I picked these 2 points. So just in the y direction, we went from positive 1970 meters to negative 1271 meters. So that's 3,241 meters of distance traveled as a crow flies. That's called the run. Slope in degrees is the inverse tangent of rise over run. So 2030 meters divided by 3241 meters, which is about 62% slope. And the inverse tangent gives us about 35 degrees of slope. That very closely matches the numbers we were getting earlier from the slope layer. So now we have a pretty high confidence in these slope layer calculations performed by QGIS.
Okay, so driving straight down a 30-degree slope is going to be tough for any rover that we may plan on using. But what if the rover took more of a slow spiral path down into the crater? What would that elevation profile look like?
I'm glad you asked, Tracy. There's an optional profile tool plugin that gives us a very simple means of choosing polyline paths, and the tool calculates elevation profiles and slope profiles for us. You can install the Profile Tool plugin by clicking Plugins, Manage, and then search for Profile. This one plots profile lines from raster layers, so that's the one. Click Install. Now we have a new button in our button bar, and we have a new menu item under Plugins. Let's run the Terrain Profile tool. This tool needs to know which layer to analyze, so select the DEM scaled layer and click Add Layer. Now we can click on the map and create a multi-segmented polyline. First, we'll just create a single line across the entire crater to see what that elevation profile looks like. Wow, that's great. We already knew that the crater was a bit over 4 kilometers deep, so the y-axis shows that that looks about right. If we switch the graph from height to slope, we can see the sensor noise that we talked about earlier, but we can also see the trend near negative 30 degrees here on the left side, and a trend near positive 30 degrees with a lot less noise here on the right side. We can actually make the slope map layer visible and use that slope map layer to choose our path, because the profile tool is configured to use the scaled DEM layer for its calculations regardless of what layer we're actually looking at on the screen. We can redo the slope that we calculated earlier at the crater's 12 o'clock position. If we drive down this particular path, we're going down about 4 kilometers in elevation, and we're driving forward about 8 kilometers. And if we switch the graph to slope, among the noise you can see it's right near 30 degrees of slope if we took this straight path, which we had calculated earlier from just a few data points, but this elevation profile tool is plotting out every single data point on that path, which can be quite useful. So let's see what happens if we take a more gentle and a more spiral-ish path down into the crater. We can try that in the profile tool. Now you can see we traveled about the same 4 kilometers in elevation, but we traveled almost 30 kilometers forward. So it's a much more gentle slope. When we switch to the slope graph, if you can see through the noise, the slope didn't go much beyond about 20 degrees using that particular path. You can export the graph data from the profile tool and work with it in your favorite spreadsheet or data analysis tool.
This is actually a lot of fun, Kurt. What are we going to do next?
We're going to crop out just Shackleton Crater from that huge data set. Then we'll add some elevation contour lines to just that smaller map. In order to crop an area in QGIS, we just select Raster, Extraction, and Clip by Extent. Then choose Draw on Canvas, and it'll let us choose the crop area with our mouse. Then we click Run, and there it is, a new map that contains just the area that we chose. QGIS created a new map layer containing the crop. We can turn off the original map layer by unchecking this box, and now we're looking at just the map of Shackleton Crater. We can now perform analysis and processing on just this subset of the original data, which can save us a lot of processing time. There's actually a lot of elevation detail here, but it's hard to see with the naked eye because the elevation detail is all shown in subtle grayscale color changes. Let's add a new layer of elevation contour lines, and that will really highlight the detailed surface topology. Make sure the clipped or cropped layer is highlighted. Then click Raster, Extraction, Contour. Now we need to decide on the number of elevation data point changes between our new contour lines. Because this map that we're looking at is still super high resolution, we want to ignore a lot of that data and create contour lines that are reasonably far apart. Remember, the units of elevation are in meters because we scaled it earlier. So, to create 100-meter contour lines, we type 100 into this field. Let's see what that looks like. Click Run. Okay, now you can see the new contour lines laid on top of the cropped elevation map. The contour lines were added as a new and separate map layer. You can change the color of the contour layer by double-clicking on the layer, and under the Symbology tab, you can choose a nice bright red color that will stand out among the whites and grays of the DEM. You can also add labels under the Labels tab. Just choose Single Labels, choose the ELEV field, which holds the elevation data, and I'll make the labels bright red also. I think that will work nicely. I'll turn off the cropped layer and examine just the contours by themselves. Look at that contour detail.
That's some amazing detail in those contour lines. Can I put that image into my excavation plan deliverable?
Sure. Let's export some images from QGIS. I'll turn on the crop layer again and then zoom out to see the entire crater. That looks nice. To export this view as an image, you simply select Project, Import Export, Export Map to Image. This dialog allows you to choose the extent or map area to export. You can choose a layer to use that layer's extent, or you can choose to draw an area on the canvas. I'll choose Draw. Then I'll select the area, and when I release the mouse button, it fills in the north, south, east, and west fields in the exact coordinates that I had selected. Click Save and choose a location and file name. QGIS gives you several image formats to choose from. Let's save another view of the same contour map. Let's zoom way in to the crater floor and save another image. Yep, that's a good spot. Now we have some detailed 2D images of the crater that we can stick into our excavation plan deliverable. Now we're going to export our contour lines and open them up in Blender for skinning. Let's export just the contour layer by selecting it, right-clicking Export, and Save Feature As. Now make sure Shapefile is selected as the file format. Then click Browse to select a location for the file and a name for the file. I'm going to call it Contours Scaled since it was derived from DEM Scaled. Click OK, and that's it. Now we can open that shapefile in a 3D modeling tool called Blender.
Blender is a popular open source desktop app that's used for 3D modeling and sculpting, 3D texturing and coloring, and 3D animation and simulation. The reason we need a tool like this in our toolchain is because we want to skin the shapefile contours and turn them into an actual three-dimensional surface. We can also apply detailed visual texture to the object within Blender, and if we desire, we can also smooth and shape and sculpt our surface all within the Blender software.
Yeah, but we're going to stick to the basics in this video. There are plenty of Blender tutorials out there though that cover the more advanced topics. Blender can be downloaded freely from blender.org. And the popular Blender GIS plugin that we use can be found at GitHub. All websites used in this video are included as links below the video for your convenience. All we need to do in order to bring our shapefile contours into Blender is click on GIS, Import, Shapefile. After selecting our Contours Scaled shapefile, we get a very important dialog box. We need to tell the plugin that the elevation value or Z value for each of the contour lines is found in the field called ELEV, which stands for elevation. When we click OK, Blender brings in our shapefile in 3 dimensions. Remember that Shackleton Crater is about 20 kilometers across and about 4 kilometers deep. If we look at the scaling values and calculated size in Blender, we can see that this 3D model appears to be using the proper scale, which is meters. Now we can skin these contour lines to make a three-dimensional surface. Make sure the shape is selected, then click GIS, Mesh, and then choose the Delaunay triangulation method. This will add a surface mesh that spans between the contour lines. Notice in the scene hierarchy in the upper right that the mesh was created as a separate object in the Blender scene, so we no longer need the imported contour lines at all. We can turn them off to see the mesh surface more clearly. Right now, this mesh surface has the basic dimensions and basic shape of the real lunar surface, although we did throw out a lot of the detail back when we created the 100-meter contours from the DEM file, which is why this surface looks a little blocky and terraced. But Blender has lots of tools that we can use to modify our mesh surface if we want. For example, we can smooth out the surface to our liking. One way we can do that is to make sure the surface is selected in the scene, then go to Modifiers, Add Modifier, and select Smooth. Then tweak the settings to our liking. You and your team are free to modify the mesh in any way that you want to make it more realistic looking. You can change its shape by sculpting it. You can add colors. You can add textures. You can add other meshes such as rocks and boulders. We're not going to go into that level of detail in this tutorial, but there are plenty of video tutorials on the internet that will go into those advanced topics.
Hey, that looks pretty good to me as is. Now how do we turn it into an actual 3D model?
Make sure the mesh surface is selected in the scene, then click File, Export, Wavefront OBJ. Select the folder and a file name. I'm going to call it Surface Scaled. And make sure to click Selection Only, otherwise the lights and the camera will be exported too. When we click the Export button, Blender will create a 3D model of our surface that can be used in all sorts of different applications.
There are also other export file formats to choose from, but we're going to use these 3D models later in our second video tutorial, which focuses on creating the mission animation deliverable. Wavefront OBJ is probably the best format for importing into the Unity game engine.
Well, that should give all teams and potential teams an idea of some of the tools and techniques that they can use to create their excavation plan deliverable for NASA's Break the Ice Lunar Challenge.
Thanks for watching our tutorial video. We hope this video is useful for any teams who are considering entering the challenge.
Yes, and best of luck to all the teams who do enter. We can't wait to see your novel and innovative solutions that each team comes up with for excavation of icy regolith at the South Pole of the Moon. Bye!